During routine conservation treatment of a portrait of a lady at the Glynn Vivian Art Gallery, the conservation team became more curious about the subject and the artist. A team of scientists from Swansea University used special analytical instruments to identify pigments used in the painting. This new valuable information and the details revealed by the restoration could enable the team to finally unlock the mystery of who the artist really is, who the painting is of, and when it was created.
My job is the easel painting conservation officer at the Glynn Vivian Art Gallery. The job involves looking after the collection of paintings that we hold here in the Glynn Vivian Art Gallery in Swansea. The original Glynn Vivian Bequest came from Richard Glynn Vivian. Glynn Vivian was the son of a wealthy family that made their money in the copper works. He travelled through Europe in the 19th century collecting art, collecting paintings, ceramics, all sorts of things, furniture, fans, enamels. But he collected over 100 paintings, and when he died, he gave his collection to the people of Swansea, along with a big lump of money to make an art gallery so that people could enjoy it in the art gallery. This painting caught my attention in the store because it had a really thick layer of yellow varnish on it, which had been partially removed on the face. It was really quite opaque and covered a lot of the details of the painting. But there seemed to be clues that it really was rather a lovely painting underneath all that dirt, and I felt fascinated to find out more about it. I discussed it with Ellie Dawkins, our documentation officer, to find out what information she had about the painting, and there was a brief entry in the accession register, just with the title and attributed to Sir Peter Lely. There was also one quite significant label on the back of the painting, which is handwritten, on which it said Queen Anne as Princess, painted by Sir Peter Lely, bought by Richard Glynn Vivian from Lord Ellenborough's sale in 1890 something, and the label was torn. So that label must have dated from post 1890 something, and we don't necessarily know that it was true. It might have been an optimistic attribution. But we felt the painting was good enough quality that maybe it'd be interesting to test that label, to test whether the attribution was correct and whether it is Queen Anne as Princess. So we felt it was worth doing some the conservation work to uncover the true colours, and then it would give us an opportunity to do scientific analysis. So it felt like really an exciting project to get to grips with, to try and find out more about this rather lovely painting. So I did a bit of research into Queen Anne because I was really fascinated to find out more about her, and it turned out that she became queen in 1702. So if the title for this painting, Queen Anne as Princess, is true, the painting has to have been painted before 1702. So we felt that was a really significant date, and if we were going to do some investigation, it would be really important to establish whether or not there were materials in the painting that came from before that date or after that date. So then I thought about the most important part of the restoration was going to be removing the varnish, because it was this very discoloured yellow-brown opaque layer which was hiding all the true colours in the painting. I did quite a few little tests and found an organic solvent that would successfully remove the varnish but didn't damage the original paint, and I just progressed with that solvent to clean the painting. So I just very gradually removed the varnish using cotton wool swabs with a little bit of solvent on them, and the solvent slowly dissolves and the original paint colours were revealed. It was like an amazing transformation. The amount of detail that we recovered, the actual original pigment colours that came back, and just like the detail in some of like the face came back to life, her hands just became more lively as well. It just brought her back to life altogether, and it was just a really rewarding treatment. During the restoration, when all the varnish and the dirt and the old fills and the old retouchings have been removed, the painting is stripped just back to the original paint. There is no extra material on it, and it's a perfect time to do some paint analysis. And if we do paint analysis and look more closely at the pigments in the painting, this can really help give information about the date of the painting and possibly about the artist. Okay, so through history, different pigments have been used at different periods, and generally, in fact, more pigments are available as time has progressed. Man has been more inventive about what pigments could be made or what could be used. The blue pigments are really interesting to look at because they have quite a clear timeline through history. And particularly at this period of our painting, around the 17th and 18th century, there's some key dates which are really important and could help us date this painting. So previous to the 18th century, the blue pigments available to artists were smalt, ultramarine, azurite and indigo. But in 1706, a new pigment, Prussian blue, was synthesised, and after that date, artists adopted it quite widely. So if we could establish whether or not Prussian blue was on this painting, it would really help us with the date. If it was on the painting, then the painting was dated after 1706. But if there wasn't Prussian blue on this painting, it would really indicate that it was painted before that date. And when I take a sample, I do take the tiniest little bit possible. It's actually only the size of, smaller in fact, than the size of a pinhead. It's so small you can hardly see it. And when I take a sample, I have to look through the microscope to see the paint sample and then put it into a teeny little tube before I send it away for analysis. The sample was then embedded in resin and ground through to get a cross-section through the paint layers. The analyst then looked at the little cross-section under the microscope, and just by looking at it in different lights and in cross polars, she could compare what she was seeing with known pigments and then tell me what pigments were in the sample. She could identify all the pigments in the sample except for the blue pigment. All the other pigments she identified were consistent with the painting being late 17th, early 18th century, but the blue pigment could have been either indigo or Prussian, but by just purely optical means, she could not distinguish between the two. So it was at this point I thought, oh, we really need to do a different kind of analysis to find out more about the blue, because we know that the blue pigment is a really important dating tool. So that's the thing we needed to find out. So I really wanted to find out more about the blue pigment, but wasn't really sure how I could do that. But luckily in 2019, we had an exhibition here of objects from the Mary Rose, and that was a partnership between the Mary Rose Trust and Swansea University. One of the scientists in Swansea University came with the exhibition. I was chatting to him about my projects, and he said, oh, I think I know somebody who might be able to help you. And he mentioned Dr. Cecile Charbonneau and gave me her contact details. So I followed this up, and Cecile was really enthusiastic and really wanted to be part of the project, and we took it from there.
I am a lecturer here at the Faculty of Science and Engineering at Swansea University, where I teach fundamentals of materials. But this is only one side of my job, actually. So the rest of the time I'm a researcher, I'm a scientist, and I work at Specific. Specific is a research center which focuses on the development of technologies that can help buildings to be more sustainable. So our vision at Specific is to turn buildings into mini power stations. For instance, today we're at the Active Office, and this is a building that's equipped with different technologies that work together to harness the energy from the sun and store it into a battery system. And this is done in excess of what's actually necessary for the building. And some of this excess energy can then be used, for instance, to charge electrical vehicles just outside the building. So my research here at Specific focuses on the development of nanomaterials, their development and characterization. And these are in the form of extremely tiny particles. These can then be used in coatings formulations that are applied a series of layers on, for instance, glass substrates or steel substrates that can be used for the construction of buildings. My scientific career actually started at the Louvre Museum. When I was an undergraduate student, I was very fortunate to do a placement there in their laboratories. And I had been working on the analysis of pigments in ceramic pieces that were excavated during the building of the pyramid, actually. So it was all extremely exciting, and that was my first sort of take into the art world. And finally, with this project, I made a comeback in this. I was finally able to go back to investigating arts and history using science. So in my current research, I specialize in the characterization of very, very tiny particles of materials. And these can be thought of miniature versions of pigments, actually. They're similar type of compounds, actually. Sometimes they're the same even that you find in paintings. So the skills I have developed in analyzing these materials for energy applications are very relevant to investigating pieces of artwork. So Jenny was interested to get a confirmation of the origin of the blue color in the portrait, and she suspected that it might be Prussian blue. Prussian blue is made with this molecule, right? Prussian blue is made of iron, carbon and nitrogen. And that's really important because iron is the reason why Prussian blue looks blue. So tracking the origin of the blue color in the portrait, what was really important is that I isolate the presence of iron in the samples that were provided to me. So if I could find iron in the composition of that sample, it would be a strong indicator that we may be in the presence of Prussian blue. So Jenny gifted me with very small samples that she had taken from the painting, and my first instinct was to use electron microscopy to look at them. Electron microscopy is the technique that's just behind me, and it's basically a very powerful microscope that makes it possible to see at extremely high magnification, down to the point that you can isolate single particulates of pigments. So the way the electron microscope works is we have a beam of electrons that's generated in this part of the instrument, in what we call the column, and it is sent onto the sample. And the sample has different reactions to it. Some of the electrons are bounced back, and this is what we use to form images of samples. And this electron beam is so energetic that it also makes the sample create or generate X-rays. And these X-rays have very specific levels of energy. So following on the microscopy observations of the sample, I decided to do some chemical analysis of those particulates and collect the X-rays, analyze those X-rays. And this is what we're seeing here. This is a spectrum showing the level of energies of X-rays that's emitted by the sample. What we can see here is that I have some lead, oxygen, and carbon, which is actually indicative of the presence of lead carbonate, or also known as lead white, which is a white pigment very much used back then. What I'm not seeing, however, is a peak for X-rays that have been generated by iron. So I know from this spectrum that iron is not present in the sample. In conclusion with this, I could confirm that Prussian blue was not the blue pigment in the painting, but I could not make any further assumptions. And based on this analysis that actually didn't give me so many clues, I knew I had to go and get further expertise and look into different area of analytical chemistry. Based on the analysis I did of the sample, I could not exactly identify which molecule or which compound is responsible for the blue color. But what I can say is that it is very light elements that compose the pigment. And based on this, I thought it might be an organic pigment. And straight away I was advised to talk to Dr. Anne Hunter, who's specialized in mass spectroscopy, and that's a technique that's particularly good at identifying organic molecules such as indigo.
I'm Anne Hunter and I work for Swansea University in the medical school. I'm in the National Mass Spectrometry facility here at Swansea University, and I'm funded by Beacon, which is a Welsh Government and European funded organisation. Cecile had been looking for what perhaps the blue pigment in the Queen Anne painting was constructed from, and she'd been looking for an inorganic pigment called Prussian blue, but she hadn't been able to find it by the techniques that she'd been using. So we discussed the possibility that it might be an organic pigment such as indigo, which was from a much earlier period. So a molecule of indigo, this is a completely organic molecule, is made up of sort of several rings of carbon linked with hydrogen, nitrogen and oxygen, and it's a highly conjugated system, and that means it has double bonds, then single bonds, then double bonds and single bonds, and so it absorbs light really well, and it absorbs orange light extremely well, orange and yellow and red, which means that it appears very blue, so it's a beautiful deep blue that is actually transmitted as all the other wavelengths of light are absorbed. So I knew that I could measure that using the technique that I specialise in, which is mass spectrometry. I work at the National Mass Spectrometry Facility, so that means we have lots of mass spectrometers, and what mass spectrometers do is that they weigh molecules. So just like giant weighing machines for very, very small bits of material. So all molecules are made up of atoms or elements that have very specific masses. When they're joined together, the molecule has a very specific mass, and we can use these machines to give us that information, which lets us know the identity of those molecules. And we do that by turning the molecules, whether they're solid materials, liquids or gases, we turn them into gases, all of them, into gaseous molecules, and then we put a charge on them. We make them into what are called ions, because when they become ions, you can move them using magnetic and electric fields. And it's basically the force that is applied to those atoms, the amount of force that is required to move them, to reach the end of the mass spectrometer and actually detect them, tells you something about their molecular weight. You're actually measuring their mass to charge ratio. And it's a little bit like, in certain types of mass spectrometers, a running race. So in order to be sure that I would find indigo in the paint scrapings that Jenny from the Glynn Vivian had supplied, she'd given me 3 very, very tiny paint scrapings. I was also given a standard sample of indigo, that's the actual pigment that is used in the paint, that's used in the paintings. And this was a good way of finding out for sure that the mass spectrometer could actually find indigo in the samples. And the mass of indigo happens to be 262 in mass, 262. But it forms what's called a protonated ion, so it adds on a little proton, which is just a charged hydrogen atom. So we're looking for a molecular weight or a molecular ion at 263 in the mass spectrometer. So that's what we did. We ran the standard, found that we could see a mass at 263, and then we were able to use that information when we ran our real paint scraping sample later on. So what I'm doing now is that it should be starting to run an analysis. So the sample is in the ionization source, and I'm going to increase the temperature of the probe in order to turn the sample from a solid into a gas, and then it will be ionized by the plasma to form the ions that we should see on the spectrum here. This is a scale of mass to charge, and this is abundance. And the higher those peaks go, that means the more ions that we've created of that mass, so the more of them that are in there. So we know that its boiling or subliming temperature is about 390 degrees. Then it should start to come up, and we're looking for a molecular weight of 263, which is indicative of indigo. So we're seeing it coming up here, a very highly resolved peak, and this is our molecular ion, a protonated species of indigo here at 263. It was great that we knew that we had ions in our paint scrapings 2 and 3 from Jenny that corresponded to the standard, the mass of 263 that we found in the standard compounds. That was great, but it isn't sufficient evidence that that is actually indigo in the samples. So in order to prove that it's indigo, we needed to do a further step, which is called MSMS, or fragmentation, where we actually take the molecule and we put a lot of energy into it, and we bump it into other molecules, and we cause it to fall apart into very specific fragments or pieces. So we went ahead and did that for our standard compound. We did it with the ions that we'd found in the paint scrapings, and we found that they matched really very well. So it gave us excellent evidence that we had indigo in the paint scrapings from the Glynn Vivian.
It's really exciting to positively identify the indigo as the blue pigment in the painting. But it just really feels like it's the start of the project, and there is so much more that we could know about it. And Cecile has other contacts who can do different types of analysis, which we really hope can give us more information about the painting. And by finding out more about the layer structure of the of the paint, how it's been applied in different areas of the painting, and then more about the different pigments across the painting, we can then build a much clearer picture of how this painting was painted and then compare it to any other pieces of research about artists of this period and paintings of this period, which might give us clues as to who the artist actually was.
Currently I'm doing a professional doctorate and I am doing forensic analysis on the degradation of organic coated steels for wall cladding and roofing. This is a digital optical microscope. It lets us zoom in really close on a tiny object and it gives us the ability to see the different layers within the coating, and you can even see some of the different particles. So this is a cross section of the blue that we've been analysing, and you can see the top layer and the coating that we've done the surface analysis of. Beneath that you can see another layer of darker blue and the ground. As part of this research, I look at the whole coating system through multiple layers, which is very similar to the work we've been doing in this study from the Queen Anne. Going forward, we're going to be looking at the other colours that are present in the painting. We're also going to be looking at beneath those colours and investigating and gaining more information on the ground layers and the paint structure and how the material and the painting was constructed.
I work with Cecile in the materials engineering department, but my speciality is actually steels. So I'm a Tata-sponsored lecturer in materials science and engineering, which may seem a long way from discovering the mysteries in the art world, but a lot of techniques are exactly the same as what I do when I analyse steel. During my day job, we use different pieces of equipment to identify what elemental compositions these materials are made up out of. So we have a portable XRF, which stands for X-ray fluorescence. This piece of equipment can actually tell you the composition of a material by just holding it against the surface and doing a 10-second measurement. This technique can be used to identify what elements are within an alloy, and we can use this to help design better steels for the future. XRF measures the reflected X-rays back, which is different to the X-rays that you have at hospital, which travel through you. And from this we can determine what elements are present in the pigments in the painting. The advantage of the XRF is now that the restoration has been complete, we can actually continue to look at the painting still. So rather than just focusing on any of the colours around the edge, we can go more towards the centre of the painting, or we can look at different colours from the blue that we were previously looking at to the reds or the pinks. The measurements can be done in situ, so the painting can be on the wall, and we can use that to determine the elemental composition of the other pigments contained within the painting, which might help tell a bigger story.
This has been wonderful, looking at a project related to art and also working with such really good scientists and art conservators, and I think it just goes to show, as I'm sure everyone else will also agree, how multidisciplinary art, science and just working together like this has been. We've all needed each other, we've bounced ideas off each other. It's been a really, really enjoyable process.
In the last few years, I didn't really meet with the art world, but I continued developing skills that are relevant to it. And this project was for me a way to go back to doing forensic science and analysis of art, which is something that was so dear to me.
This collaboration has been really fascinating, and what I've really enjoyed about it is that it's so multi-stranded. So I feel privileged that I could do the conservation work, which has really revealed the quality and the colours of this painting. And the scientists have all brought their different aspects and different skills which can look at this painting in completely new and different ways. And I hadn't realised before how many different types of ways that we could look at the painting, which would all give us different information. And then if we add in art historical research and stylistic analysis by experts, I feel we're going to have a whole new layer of understanding and insight into this painting. The pigment identification is actually only one part of the puzzle. Now the painting is cleaned, I would really like experts from the period the 17th, 18th century to look at our painting again. Now all the details show and the colours show, to give us another opinion on who the artist might be. The other strand that we need to follow is provenance. So it's maybe from that label, the very first label that I talked about, showed that Richard Glynn Vivian bought the painting from Lord Ellenborough sale. So we need to try and track down any archival information about that sale to see if this painting is listed and look at anything to do with that estate. And I really believe this will finally unlock the mystery of who the artist is and when the painting was painted.